Hello, my name is Richie Wong, and in this report we will analyze how various equations of states can be used in steam turbine analysis. To introduce the team, from left to right, Austin Peters conducted research on various types of steam turbines and selected one for this report. He will also discuss our results later in this presentation. Next, Tate Smith worked on developing a working code which will use three equations of states, and he will break down the code later in this presentation. Finally, Richie Wong also helped with the code and will go through the technical report. The turbine that we use comes from the American McCann Company, which, although went out of business in 1986, we still believe that the turbine they use is relevant to our current report. The goals of this report seeks to analyze the validity of various equations of the states, such as the van der Waals, Redlich-Kwong, and the Peng-Robinson. Then we will compare values such as work and efficiency from our code to those in the report using Jupyter Notebook.
This is our Redlich-Kwong book. In the second cell here, you can input your constants along with pressure and temperature from states 1 and 2. And this cell here has the Redlich-Kwong equation of state solved for V, and this next cell uses that function in fsolve to solve for V1 and V2. This cell sets up your departure function enthalpy integral and then gives you the departure function enthalpies for states 1 and 2. And finally, this cell uses a heat capacity integral along with your departure function enthalpies from before to solve for work. This is our Peng-Robinson book. In the second cell, again, you can input your constants along with pressure and temperature from states 1 and 2. And also we have reduced temperature and kappa and alpha. This cell has the Peng-Robinson equation of state solved for V again. The cell uses fsolve on this function to solve for V1 and V2. Again, the cell sets up your departure function enthalpy integral and solves it for states 1 and 2. And this one uses those departure function enthalpies in the heat capacity integral to solve for work. This cell sets up the integral to solve for departure function entropies and solves them for states 1 and 2. This whole function is to solve for your total change in entropy using this heat capacity integral again. Then we use fsolve on this function up here to find the temperature at which change in entropy is 0. We use that temperature to solve for work using the heat capacity integral again, and that gives us our ideal work. And then finally, we use that ideal work to solve for efficiency.
The results of our code were based off of the throttle point, or the point of the inlet steam to the extraction point. For the generated work, this was given by the report to be about 3,230 kilowatts. Using the Peng-Robinson equation of state, however, we got approximately 3,440 kilowatts, which accounted for an approximate 6.56% error. On the other hand, using the Redlich-Kwong equation of state, we got about 3,170 kilowatts, which only accounted for an error of about 1.83%. For the efficiency of the turbine, the report gave a value of about 84% based on an isentropic or ideal work of 3,842 kilowatts. Using the Peng-Robinson equation of state, we got an efficiency of about 92.7%, which was about 9.2% off of the report data. And this was based on an isentropic work of about 3,700 kilowatts, which was about 30.36% off from the ideal work that was used in the report. Using the Redlich-Kwong equation of state, again, we got an efficiency of about 85.4%, and this was based off of the same isentropic work, and this only accounted for about a 1.6% error. So what did or didn't work with our code and why? As you saw for both the shaft work and efficiency calculations that we made using our equations of state, the values that we got were pretty similar and accurate to what was reported in the technical report data. In terms of the shaft work, we account this similarity to the dependence on the change in enthalpy between states in both of these calculations that we used and what was used in the technical report. In terms of efficiency, again, there was a similar method of calculation. Instead, this time, the calculation for the efficiency relied on the isentropic entropy for both of the calculations in the report and what we did. However, in both cases, we saw that the Redlich-Kwong equation of state gave slightly more accurate answers, and that the percent error was slightly lower than for the Peng-Robinson, and we account this to the Peng-Robinson being specifically developed for natural gas systems in which the molecules within these systems are non-polar. And since steam is the focus of our system and the water molecules are polar in steam, we think that this may be the cause of these slight inaccuracies.